With the hint at the beginning of class, finishing up real quickly, 9-3. We were almost there, but got a little bit stuck. You guys should have brought down that n minus 1 like we were talking about. You had that ln of 3/4 that was kind of messing things up a little bit as we were trying to get to n. So we could multiply by 1 over ln of 3/4 to get rid of him, or another way of saying it is we could divide by ln of 3/4. On the other side, we could do 1 over ln of 3/4 times ln of our 10.125 over 32. What's the last step in getting n by himself? Adding 1. Plus 1. Plus 1. N is equal to, what you guys get as you plugged into your calculators? 5? 4.1? It's supposed to be a whole number in y. So I'm a little worried. Why does it need to be a whole number? What does n stand for? Oh, come on, sequences and series. We know. What does n stand for? The term, right? The first, the second, the third, a sub 1, a sub 2, a sub 3. Are there any fractional n's in sequences and series? And the answer is no. We have to have whole numbers. So I'm quickly plugging and chugging myself to make sure we didn't get a decimal. Oh, typo. It happens. Struggle. And yet, is it a struggle?
Yes.
It can be. But aren't weaknesses also blessings? Count it all joy when you fall into diverse temptations? That's a hard one. James is just a hard book. It's an important one too. How to behave under shock. Is it really about behavior, or is it about more what to be thinking and reminding ourselves of? What truth to be remembering? Finding the infinite sum. We gotta finish 9-3, we're going on, but lots of life lessons in between there somewhere. Sums of infinite geometric series. Sums of infinite geometric series. Why are they infinite? Because it says so. Okay, cool. In the notation, why are they infinite? Because it shows so, right? There's infinity, sideways 8. How do you guys write your infinity? Do you write it this way? Okay, good. Some people do. That way, right?
Yeah.
Okay, good. Even though you do your sigmas, honey. So like my sigma letter. Anyway. Yes. So I'll help. There you go. Okay. We are talking specifically about geometric series, right? Remind me real quick, what's the pattern in geometric series? Series adding together terms. Geometric, what does that mean? Multiplying or dividing, which is multiplied by the reciprocal. By a constant, which is called the common. That's for arithmetic. Common. How do you find multiplication? You divide, and what are divisions or fractions called? Ratios. Common ratios. Okay. So multiply by common ratios. Yesterday, wait. Didn't we talk about this word yesterday? I think we did. Right? What was I doing when I talked about converging? there was a stool and I was on a certain end and I was one arbitrary unit away and I was stepping using what ratio? 1/2. I was taking up half the remaining space of the stool every time I stepped, approximately as best I could. And so we saw the distance I was covering, 1/2 plus 1/4 plus 1/8 plus 1/16, and we said, ooh, that could go on infinitely long, right? That could go on infinitely long. However, when I asked you guys, okay, if you add infinitely many times, what's going to be happening to the sum? Most of you started with, oh, it's going to get bigger and bigger and bigger and bigger and bigger and bigger. But then we said, wait a minute, how far was it from me to the stool? 1 unit. And was I ever going to go past the stool? No. So as I stepped and stepped and stepped and then theoretically kept stepping closer, which I couldn't do in all actuality, talking about that too, what was going to happen to that sum? It was going to converge. It was not going to get infinitely big. It was going to get closer and closer and closer, similar to an asymptote, but never reaching. Converging to, getting closer and closer to the one arbitrary unit. So, here's the idea. With geometric series, what's the difference between the one that I showed yesterday? Can I call that the stepping to the stool example? Stepping to the stool example, otherwise known as Zeno's paradox. Who wants to be super spiffy? Just kidding. Zeno's paradox is pretty cool too. Zeno, I think it's X-E-N-O if I remember right. It's been a while since I've actually spelled it. I think it's Zeno's paradox technically. Might be a Z. I'm second guessing myself. But a stepping to the stool example, that was 1 plus 1, nope, didn't start at 1. Started at 1/2, right? 1/2 plus 1/4 plus 1/8. Because the distance from me to the stool was finite, this sum will converge. Another one that we talked about, a convergent sum. Stepping to the stool, that infinite sum is going to end up equaling, I need more room. Don't worry, I got this. That infinite sum is going to equal 1. What other one do we talk about? Repeating decimals. And this was actually in section 9.1. It's been a little while. Repeating decimals. Yeah, remember this one? We could do 3/10 plus 3/100 plus 3/1000, which we talked about was 0.3 plus 0.03 plus 0.003 plus 0.0003. That ends up being 3 point, no, sorry, 0.33333333333333333. It can keep on going infinitely long, but it's still converging to a finite sum of 1/3. And I think in homework, didn't you guys have the 0.111, the 191? Thank you. So what's the difference between these convergent sums and between one that is, it's not just a movie. This divergent sum. This gets a little crazy. But what if I was to say something like 1/3 plus 2/3 plus 4/3 plus 8/3 plus, oh man guys, they're still fractions, right? Okay, so it's convergent. Nope. Not convergent, it equals infinity. What? No, I'm not going to say what level of infinity. Once again, we've kind of briefly talked on the different levels of infinity, of different magnitudes, different greatnesses, different beating each other along the path or the way to infinity, which is kind of complicated. But what's the difference between the first two, which we would say are convergent series, and the last one, which is a divergent series? What's the patterns? And how do they differ? Good. Karina's saying on the first two, the numerators are the same, and the last one, the denominator is the same. That's a difference. That's a key difference. It's not what I'm going to write up here, but it does kind of lead us closer to the idea.
The denominators are growing.
On the bottom one, the denominator is growing as the numerator stays constant. On the bottom one, the denominator is the same. What happens as the denominator grows? Look at this one as an example. What happens to the overall separate values as the denominator grows? It gets smaller. Once again, we have to be careful of that. I've talked about how 1 over 2 plus 1 over 3 plus 1 over 4 also equals infinity, which is confusing. That's more of a BC idea. But, coming back. For geometric series specifically, can you guys tell me what the common ratios are of each? What's the common ratio for the stepping to the stool one? 1/2. I was multiplying by 1/2 every time. What's the common ratio for the repeating decimal one? Careful, not 1/3. 1/10. What's the common ratio for the last one? 2 over 1. What's the difference between multiplying by 1/2, multiplying by 1/10, and multiplying by 2? The last one, every single term is growing. If you add growing numbers, what's going to happen to the sum? Make sure your phones are put away. I don't want to see that. Not in my class. Growing. If I add growing numbers, what's going on? Just think of it this way. What's 1 plus 2 plus 4 plus 8? Plus 16. Oh my goodness. I'm adding bigger and bigger numbers. What's going on to my overall sum, my partial sums? They're getting bigger and bigger and bigger and bigger. And how long are they going to get bigger for? Infinity. Well, if they're getting bigger and bigger and bigger, do you see why I wrote infinity and why I'm saying divergent? It doesn't mean divergent in that they're not all headed the same place, which is infinity. It means divergent because it is not converging to a sum, a finite number. Okay? So let's go ahead and talk about this up top. Ready? The sum, the infinite sum, will not exist when, for a geometric series only, the common ratio, I could say it snazzily, the absolute value of the common ratio is greater than or equal to 1. But here's another way of saying it's a little bit more common sense. R is in between and equaling -1 and 1. The infinite sum will not exist when R is... Oh, I just put that backwards. Oh my goodness, I totally put that backwards. Fail, 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 fail. It's a momentary fail. Much better than an infinite fail. R is greater than or equal to 1, or R is less than or equal to -1. Whew. Don't worry, it's coming. Have faith. There we go. In a computer, probably not a good idea, but know what that provided. R is equal to 2, which is greater than 1. Okay, I get it. It fits the rule, right? It didn't work. But what about if R was equal to 1? Why wouldn't that work? Be adding the same number over and over and over again. As you add the same number over and over and over again, what's it still doing? Yeah, it's going to be growing. Good, it's going to be growing. So R has to be, or if R is, I should say, greater than or equal to 1 or less than or equal to -1, there is no infinite sum. The best way to answer that problem would be, ready? Divergent. If infinite sum does not exist, we explain or we say that that series is divergent. Hi, girl. What will we do with that? That's a very good question. I know, right? Okay. When does the infinite sum exist? Every other time. And what's every other time? Flip it. But not or equal to, because the or equal to is divergent. And write what I tried to write last time and it was wrong. infinite sum does exist. And we can call that convergent. Guys, once again, this is only for geometric series. I've kind of tried to introduce to you guys since you're in Honors Pre-Calc that there are many other ways, many other types of series that we cannot use this trick, this clue on with the divergent and convergent. The biggest topic, the new topic in Calculus VC, Calculus Level 2 that comes up has to do with sequences and series and whether they converge or diverge. It's a big idea. It's a hard idea. It's an involved idea. But for geometric series, it's an easy idea. We have these two rules. If R is greater than or equal to 1, sorry, I should say absolute value of R, which means greater than or equal to 1 or less than or equal to negative 1, the infinite sum does not exist. DNE, aka the series is divergent. If R is, absolute value of R is less than 1, or the magnitude of R is less than 1, so R is between negative 1 and 1. The sum does exist. The series is called convergent, and this is how you find it. Go. Formula for the infinite sum. If it exists. True, do I have to add that? The formula for the infinite sum, if it exists. And just in case you want in one nice little place that you can highlight with a pretty box around it, when will it exist?
With R is no 1.
When R is not 1 or negative 1, but it's in between. If you want to be super snazzy, you can do interval notation. That's like the olden days, right? Or should I say the future days? Ooh. But if R is between 1 and negative 1, not including, only then will the infinite sum exist, and this is how you find it. Now, since we're talking about the future, in lots of ways today, can I show you something else from the future? Has anybody seen any calculus kids homework and seen something with an L and an I and an M? Have we seen it this year yet? It's called a limit. And why am I putting the snazzy notation in front of this S sub n? Isn't this S sub n a partial sum? Doesn't S sub n stand for partial sum? Right? Partial sum of the n, or the first n terms. So if there's S sub 2, would be the first 2 terms added together. S sub 10, the first 10 terms. I don't like just using S sub n equals an infinite sum because S sub n by definition says you cut it off. We're not cutting it off. We're going to forever. To infinity and beyond, we're all Buzz Lightyears. So, dream come true. Coming back. Why am I putting this snazzy calculus notation in front? Limit as n approaches. Hey, wait, haven't we talked about the arrow before though? That's not new, right? Isn't that from chapter 1, 2, something? I don't know. We talked about approaches when we were talking about like asymptotes and stuff. And the end behaviors of functions, whether the function was going to infinity or negative infinity. So the little arrow shouldn't be scary. That just means approaches. As n approaches infinity. So what am I saying? Am I cutting n off at 2 or at 10 or at 50? No! What am I telling that n to do? You go to infinity, n, right? Why? I want the infinite sum of the infinite number of terms, aka I want to go to infinity. So I have my n go that way. Does that kind of make sense? S sub n says cut it off. The little limit says no you don't, keep going. How? By telling the n what to do. And what is it looking for? The limit. Wait, what's a limit? Some sort of restriction, like yesterday the stool. I could keep stepping and stepping and stepping theoretically forever if I had infinitesimally small toes. Anyway, I could keep stepping and stepping and stepping and stepping and stepping close to that stool, but what was I never going to go beyond? What was my limit? The stool. That's the idea of converging. Converging to a limit. Now, do you guys know everything in the formula for you to be able to plug in? What's a sub 1? First term. What's r? common ratio. We're good on plugging in, right? I'm just introducing this super cool calculus idea of a limit at the same time as showing you a formula. Why? Because this is one of the best times to introduce some of those calculus ideas. Geometric series, convergent geometric series when r is in between 1 and -1. Now, just because I'm a calculus teacher, just because this is honors pre-calc, we're going to talk more about limits in just a second. But first, let's do some examples with those geometric series ideas, okay? Hence why we're taking more time on section 9.3. Find the sum. Not the nth partial sum, not the fifth sum, not the sixth sum, not the 10th sum. The sum of the infinite geometric sequence. Let's contain infinity in God. We'll see if it can be contained in a finite number. And if it can't, as some things cannot, then we'll just say divergent. It's beyond our scope. What do we have in number 76 up there? How come that's a series? It looks a whole lot different than number 80. Sigma notation, aka it's a summation, aka we're adding together stuff. And what's the stuff that we're adding together? If you guys want, you can use this and memorize this, or didn't we talk about yesterday we can actually start plugging and chugging and look like it in this kind of form? It's called expanding the summation. Where would we start plugging in? Our lower bound, which is 0. So we'd have 4 times 0.2 to the 0 power plus, what's our next one? 4 times 0.2 to the first power, right? Plus 4 times 0.2 to the second power, plus we could keep on going. But let's make this look prettier. What's anything to the 0 power? What's 4 times 1? 4. What's 4 times 2/10? Ooh, 4 times 1/5. Can we do that? Ooh, that's nice. What's 4 times 0.2 squared? 0.04, that's gross. What's 4 times 2/5 times 2/5? Oh, isn't that 8/25? Oh, pause. What did I not multiply in this guy? We should sue. Not we, I guess you, but don't please. I should have written it out. Exactly. I was going to wait a second before I apologize to one more time. Yes, I think it's a Friday, and I thought it's a Friday for the last 2 days. Anyway. Woo! 2/10 is 1/5. That's why things are getting weird. All right. Now we have it all worked out. 4 plus 4/5. I was right. Plus 4/25. Plus 4. Can we tell what the next one is? 1/25. Question. I know my common ratio. It is a 0.2, but what's another way of saying it? What do you think about the r as being 0.02, or what do you think about from the original formula, or what do you think about it as being 1/5? My question to you is, does the sum of the infinite geometric sequence exist? Don't tell me what it is. Does it exist? Yes. Why? 1/5 is a little one in between 1 and -1. That's convergent. So I could say, yes, it's going to be converging if I want to be snazzy and describe it. But how does it converge, or what does it converge to? The limit as n goes to infinity. Yes, I want you to write it, of s of n, the whole thing, not just what the book's going to say, is, what's the formula say? A sub 1. Who's a sub 1? 4. Where do I start? 4. Times, what's my formula say? Exactly. Why do you think I put it into a fraction? Because I thought that'd be easier to solve. 1 minus 1/5 would be 4/5. Isn't that the same thing as 4 times 5/4? And it's not the same thing as 5. Dun, 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 dun. What did I plug into, though? I didn't make it up. I plugged into my formula. A sub 1 times 1 over 1 minus r. So question, how about this guy? He's geometric, I think. They told me he was. But my question to you is he convergent or divergent? But you cannot answer that until you think, what is his common ratio? It's a bit of a struggle. It's a little bit hard to see. And if you do not like it, yes. Can't you divide it? So they say find the common ratio. You can take the ratio of the second over the first. Let's see if it works. I think I would multiply top and bottom by, because I don't like this denominator. I'm going to get rid of this guy. Get rid of that guy. When I simplify, oh, maybe it wasn't as complicated as we thought. What's my common ratio? Negative 1/5. Oh, guys, ridiculous. This is, you should totally assume now. What did I write wrong? Who is he? You guys feeling better about the silly mistakes you make on test now? No? Okay, never mind. Same. The process was still good though. Now I can reduce. I have a 1 and I have a 6 and I have a 1. Nope, that's not going to work. I have a, yeah, that works. 1 and 5. All right, go team. Good thing you guys are honors. You actually double check me, unlike regular. They just sit there and stare. Some take notes. So, just kidding. Most. Now wait a minute. It's a fraction. Ah, sweet. It's convergent. Let's keep going. Yeah, exactly. Come on. If you see a mistake, let me know. That doesn't work. Negative 6/5 is technically, if you want to think about an absolute value of negative 6/5, that's positive 6/5. Isn't that greater than 1? Greater than or equal to 1? Yeah, either way, it doesn't matter. Doesn't work. What doesn't work? The sum. Why? Because this series is divergent. Therefore, we can say the infinite sum, the limit as n goes to infinity of s of n. Let's just say d n e for right now at our level. This is a little bit harder because you have positive, negative, and oscillating sequence. Sorry, series. So we'll just say d n e because it doesn't exist. Dun 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 dun. Dun dun. Do you guys see how it might be important to highlight almost everything on this page? Yeah. Almost everything. The examples were just for sake of illustration. Now hold on. We talked about limb though. We talked about limb though. Just kidding. Limit. Don't say limb. That's awkward. One sign of knowing the math is that you know how to read the math, right? Not like where that placement was. The limit as n approaches infinity of s of n, just put parentheses to make sure that you distinguish between the two. When you need to approach infinity, take a limit. Now, that's not the only kind of limit. You can actually take the limit as n goes to any number, any constant, any vertical asymptote. You can also go to infinity and to negative infinity. We're just introducing this idea of a limit. Asking the question, as n goes to wherever you're sending him, to the right, to the left, towards a number, from above, from below. As n approaches a number, what is the function that is inside doing? Is it getting closer and closer and closer to a number, or is it not? So, if you guys did not yet, write down the notation. This is, once again, if you already wrote it down, don't write it again. The limit as n, can I say APP, approaches infinity. Let's not put it there. of key operative math term. The nth partial sum, technically, in this case, or of S sub n. That's what I'm saying. But let's go ahead and see if we can actually take the limit. You're like, no, we already did. No, we didn't. We memorized the formula and we used it. Let's see if we can take the limit. Let's see if we can do the math behind the formula. What? Here, you ready? This is not for the faint of heart. Hold on, pause. Give everybody in your group a high five. Tell them, let's go. Gotta get pumped up just a little bit. Come on. Oh, come on.
Sorry.
Come on. I've seen you out in the fields. Seen you out in the courts. Let's go. Come on. Oh my goodness. Fail. The enthusiasm is gone. Guys, this is a big day just because it's hot in here.
It's not even hot in here. It's just like
It's cold right now.
not right now. It was
Okay.
cold. Only around.
Okay, now you're awake. Pause. One more time. A high five. A hardcore high five. Everybody in your group, go. Come on. Come on. I need to hear it.
Yes, three.
Let's go. 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 All right. Here we go. I'll even do this for you. Cheering you on. I was cheering you on. Okay, you ready? The limit. Now, hold on, pause. Do you guys see how there's like not a cursive L right here? There's not a cursive L up there. Why am I doing a cursive L? What do you think? So it doesn't look like an absolute value bar or like a 1 or like a, well, it's supposed to be an L. It gets confusing, right? So the limit, as n goes to infinity, we're doing the math, guys. Hold on. We're doing the math. We're not just memorizing some silly formula. Who is S sub n? Do not tell me A1 times 1 over 1 minus R. That is not S sub n. Who is the nth partial sum formula of a geometric series? That's good. Exactly. That is S sub n. Another reason why I needed to correct what was written. The limit as n goes to infinity of S sub n is the limit as n goes to infinity of A sub 1 times 1 minus R to the n over 1 minus R. There we go. That's S sub n. Now, how on earth does this turn into what we have on the previous page for the infinite sum of this series, if it exists? Pause. We do need to think about when this will exist and when this won't exist, because R is a variable, R is unknown, right? What did we say about what's going to be true if this exists? Yeah, the magnitude of R is less than 1, hence R is in between -1 and 1. True, true, true. Okay, now hold on. What happens, I want you guys to get your calculators out. What happens, calculators out, I'm not kidding, calculators out. I want you to choose in your mind without telling anyone else, choose any number that fits in that category. It has to be a fraction, PS, or a decimal. Any decimal, any fraction, positive or negative, that is less than 1 or greater than -1. It can't be big, it has to be small, small in magnitude. I'll give you an example. 1/2 is a great one, so is -1/3. Pick your own though. Pick your own, put it in your calculator, that'll be to the first power, right? Just hit enter. Put in your fraction, put in your decimal, hit enter, that's the first power. Where is R being plugged in where there is also an N? Do you see it? Where does the N show up in the formula? Right there. How do you simulate, start making that N approach infinity? Just take one step at a time. Square it. Cube it. The next step. To the 4th power it. The next step. Hey, be crazy. To the 10th power. Next step. Be really crazy. To the 50th power. Next step. You're making N get bigger. Take whatever number you chose in between 1 and -1. Square it first. Then, don't cube the next one. Take your original, then cube it. Then to the 10th power, your number that you chose. Then to the 50th power. All of your numbers were theoretically different And yet, as you keep going higher and higher and higher in the powers that you are raising, all of your numbers should be getting closer and closer and closer to 0. Am I right? And if you go really crazy, you might have something like e negative 100. What does scientific notation times 10 to the negative power mean? 0.00000000, however many negatives you have, right? All of your numbers are approaching 0, if you did it right. Do you guys agree? So wait a minute. What's going on with any common ratio as n approaches infinity? This value is approaching 0. And so we say this value, r to the n alone, converges to 0. We replace, we substitute. This is what taking a limit does. We replace or we substitute a 0. So kiddos, what happens when we replace or substitute a 0? Dun, 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 dun. You just solved your first limit. Go team. Now, at the end of the day, am I going to force you on a quiz or a test to show me all of this? And the answer is no.
Yeah.
But do I need you to properly state what notation an infinite limit should have? The answer is yes. And do I need you to know how to find the infinite limit provided it exists? And the answer is yes. Are we tracking? Okay. Long story short, all of that is once again summarized in the table on the page before. However, I want you guys to write it properly. And just a few, you figured out, oh, that's where the formula came from. Anyway, long story short, yes, I know. We did go over today. Ooh, that'll be fun. Let's see how you do in homework on that one. Homework number 55, section 9.3 is totally due tomorrow. Hopefully you fully attempted it by tomorrow. So, to end today, since we're almost done, my question to you is, how do you expand a plus b to the first, second, third, fourth powers? Yep, you FOIL. So this one, just a plus b. This one, you FOIL, you get a squared plus 2ab plus b squared. Don't kill a puppy. This one, guess what? You would have to do that polynomial multiplication 3 times. But guess what? There's a simpler way to figure out what's going on. And guess what? I can keep a certain pattern going for as long as I need. Is this faster than doing a plus b times a plus b and that times another a plus b and that times another a plus b? The answer is yes. Whoa! How did I do that?
Tune in tomorrow.
Pascal's triangle, is that a thing? We'll see you tomorrow. Bye, Focus. Chandra,